Let's begin chapter 14, and we're talking about oscillations, and in particular, we're going to be talking about. So, going through the slides for chapter 14, um, there's a lot of things in nature that are explained by the equations that describe simple harmonic motion and simple harmonic oscillators. And some of them are somewhat surprising. So, for example, walking in some sense is a form of oscillatory motion. Um, Things like going on a swing. Of course, sound involves a type of wave, an oscillating wave in compression of air molecules or compression of the air density that results in a vibration of your eardrum, and this is how we hear sound. If you get into physics 2, then we'll discover that light is also a form of wave. It's a wave of electromagnetic fields. So far in this class, we've taken a look a little bit at springs and the stored potential or elastic potential energy in springs. We haven't really played around with the motion of springs very much, so we'll take a look at that in this chapter, and we'll see that springs, if allowed to move, if you put a mass on a spring and pull it and let it go, and there are no other forces acting on it, that it'll undergo oscillations in the same sort of simple harmonic oscillatory motion. So let's start just with a reminder about springs, that springs have a force that pulls them back towards their equilibrium position. Because of everything that's been going on this semester, we skipped chapter 8 material, but this equation here shows the restoring force in a spring, and that force is proportional to how much the spring has been displaced from its natural equilibrium position. So K is a spring constant, so that just has to do with what kind of metal it's made of, how thick the wire is, how tightly wound it is, and everything. That's just a constant about the spring. And delta X is the displacement from the spring's equilibrium position. So you just take a spring, you don't do anything with it, it's got a length. Then if I stretch it or compress it, the amount that I'm stretching it or the amount that I'm compressing it is delta x. And what this equation is showing is that FSP is, that's both the force required to stretch or compress a spring by an amount, by a distance delta x, and is therefore also the force the spring exerts back on you from Newton's third law. So that force is the force that's shown here in the slide, that the spring is pulling back on you towards that equilibrium position. So that's what that minus sign in that equation is showing, is that the spring force is trying to go back, trying to negate that stretching or compression that you're doing of the spring. So it's in the opposite direction of the delta x. So there you can see that the blue arrow, delta x, and the red arrow for the force are in opposite directions. And that force is called restoring force. Because it's trying to restore the spring to its equilibrium position. This particular expression, this restoring force for springs, FSP, is proportional to delta x, and this proportionality is going to be an important point later. So let's take a look at some examples, some other examples. Here we see a ball in a bowl, and if you lift the ball up and still on the inside edge of the bowl and let it go, it's going to oscillate back and forth. And in this case, there's a restoring force as well. And the restoring force in this case is the component of the object's weight that is directed back towards the equilibrium position. And as the illustration shows, the farther away it is from that equilibrium position, the greater is that restoring force. Of course, if you let it go, when it gets to that equilibrium position, the force vanishes. At that point, gravity is just going down, and let's just do another example of restoring forces. We have a bowl and a ball, and so there's the normal force this way, there's weight that way. This thing is going to move this way. If it gets to the bottom of the bowl, I should play around with my fun colors here. At this point, weight is down, the normal force is up, the acceleration is 0 at equilibrium. At the equilibrium position, the acceleration is 0, but the velocity is not 0. It's cruising along this way with some significant velocity, so that means it's going to overshoot that equilibrium position, and it'll roll up the other side of the bowl, at which point there will be a restoring force bringing it back down, and this is why you end up with oscillation. Now, we're already familiar with some of the terminology that we use to characterize oscillatory motion. T, big T, let's go back to black. T is the period of the motion. So for our example of that bowl here, let's do this. Our ball goes down this way, up to here, and it's going to come back down. So T is the time to go, let's label this as position A, B, C, from A to C and back again. So a frequent mistake that's made is to think that the period is just the time to go 1/2 of the oscillation, but you need to have all the way back to your starting position so that the cycle can start over. F, the frequency, is just 1 over T, so it has units of 1 over time. If T is in seconds, the unit of that is a hertz, as illustrated here. So Hz is the abbreviation for hertz, which is just 1 over seconds. So let's take a look at the particular case of simple harmonic motion, and that's the particular type of oscillatory motion that we're going to be talking about. And simple harmonic motion, the position of the thing that is oscillating is described by a sine curve. Here they're saying cosine. There's no difference between sine and cosine. They're just shifted left or right relative to each other. So if the oscillation is simple harmonic motion, it's going to be a sinusoidal oscillation. Be sure to check the videos that are provided in the textbook. So examples of those, this ball and the bowl that we've been illustrating or talking about here is one such example. Another example is mass on a spring. Another example is a pendulum. As long as the pendulum is not uh, going through crazy angles, but if, like a pendulum and a clock, follows simple harmonic motion sound waves that we experience. And then, as I mentioned before, so is walking. So the key thing about simple harmonic motion is that the restoring force is proportional to the displacement. So if the restoring force is proportional to the displacement from equilibrium, then motion can be described by simple harmonic motion. And that's good because simple harmonic motion is, as the first word indicates, simple. It's relatively straightforward to describe. So what does this mean? Restoring force proportional to the displacement. Just come back to the spring and the equation that you see on the slide here. Any oscillating system has an equilibrium position, meaning if you didn't do anything with it at all, it'll just sit there. So take a bowl, put a ball in it, set it at the bottom, it's just going to sit there. But if you drag it up the side and let it go, then it's oscillating. So the equilibrium position is just where things want to be, and if nothing happens to it, it's just going to sit there. Same with a spring. If it's displaced from that equilibrium position, it will oscillate around it, and that oscillation will be described by the equations of simple harmonic motion, which can be explained by sine waves and cosine waves. If the force that's trying to pull the thing back towards that equilibrium position is just linearly proportional to how far away it is from that equilibrium position in the first place. So that's what's shown in the slides here with the spring example again. The restoring force is linear, the net force is towards the equilibrium position, and it's proportional to x, the distance from the equilibrium position. And what do we mean by saying that it can be described by sinusoidal? If you look at a spring, block on the spring as shown in this example here, it's just oscillating back and forth. But if we plot the position of that object on the end of the spring as a function of time, then we get a sine wave. So in this particular example, they're having the time go down, and the object then traces out a sine wave as a function of time. Okay, so let's get forward to our own examples. This particular example, take a vertical spring, put a mass on it, and it hangs. And once it's hanging, it's got a new equilibrium position that's shown here. We see a free body diagram for that mass on the spring. And then we can use this is how weight scales, spring scales work like at the grocery store. You put your fruit in the thing and it stretches the spring by a certain amount. It just measures the amount of that displacement. That distance is proportional to the force that is applied to it. And the force, of course, is just the weight of your apples or whatever it is you're put in there to weigh at the grocery store. And so it just has to convert that distance to mg, the weight, and that just depends on what the spring constant is, as shown here. A pendulum is another example. It's a little bit different because of the circular motion of the pendulum, and the pendulum motion is only a simple harmonic oscillation if the angle of displacement is small. And here's why. The force, the component of the force that's bringing the pendulum back towards the equilibrium position, as shown in the slide, and I'll try to sketch it here. We've got what are the forces that are acting on this thing? Tension up towards along the string, and weight down, but the motion is this way because it's constrained. The string can't get longer or shorter, and so the component of the velocity or the component of the force of gravity towards the equilibrium position is mg sine theta. And that should look familiar if you remember when we had things on ramps earlier in the semester. The component of the weight down the ramp was always just mg sine theta. The acceleration down the ramp was always g sine theta. And so that component sine theta is not exactly the displacement. We want our restoring force to be proportional to the displacement. But if theta is small, then sine theta is very closely equal to theta, again, using radians. And you can try this out on your calculator. Switch your calculator to radians modes, enter 0.05, take the sine of 0.05, and you're going to get 0.05 also. In other words, as what's shown here, for small theta, that means theta very much less than 1 in radians, then sine theta is approximately equal to theta, and then the displacement of the pendulum is approximately theta. This sine theta in the restoring force, we can replace it with theta, so then it is proportional to the displacement from the equilibrium. And so we have a simple harmonic motion for a pendulum as long as theta is a small angle.